This is Origin Stories, the Leaky Foundation podcast. I'm Meredith Johnson. Today on the show, we're looking at how and why humans are the musical ape. But before we get started, I want to thank our new podcast donors, Stacy Love, Stephen, Mark, Michael, and our other new supporters who wanted to stay anonymous. We're so grateful for your support and your kind comments. If you'd like to support the show and get a shout out on our next episode, please click the link in your show notes right now or go to leakyfoundation.org/origin stories. Your one-time or monthly tax-deductible donation will be quadruple matched. So if you give $10, we'll get $40 to help us tell new stories about what makes us human. Now, on with the episode. Music is universal in every culture around the world. In fact, no human culture has yet been found that doesn't have music. Our prehistoric ancestors made music too. The oldest undisputed instruments in the archaeological record are two 42,000-year-old flutes. One is made of mammoth ivory, and the other was made of a bone from a swan's wing. Today, music is all around us. We use music to express our emotions and heal our broken hearts. And it also gives us joy and pleasure. But why? What is it that makes us musical, that allows us to hear sound and experience it as music?
We use music to enhance our moods. Or if we're sad, it helps us to sort of console our mood. And if we're very enthusiastic and we put on enthusiastic music, it releases the energy.
This is Henkjan Honing. Henkjan is a professor of the cognitive science of music at the University of Amsterdam. And he's on a quest to understand how humans are able to perceive rhythm and pitch and tempo, how we have what's called musicality.
Most people, if they think of musicality, they think about something special. Somebody is very musical. An exceptional singer, an exceptional musician, or an exceptional talent to listen to music or something. But it is more than that. Musicality is the capacity for music. So the talent that we all share, most of us have that, is to be able to perceive music and to appreciate it.
Henkjan compares our musicality to our capacity for language. Music means something to us. But when Henkjan first started trying to understand musicality, he wasn't a scientist. He was a musician and a composer, fascinated by computers that could make sound and music.
And I thought that would be the future. So I thought this machine was going to change everything. I thought the piano would be old-fashioned, violin would be old-fashioned, it would be the computer in the future.
When he arrived at the Stanford Center for Computer Music and Acoustics in the early 80s, Stanford had a new kind of computer called a Samson box. The Samson box looked like a big green refrigerator, but it was cutting-edge technology that could be programmed to make music.
Think about what you want and then explain to the computer what you want, and then the computer would do it for you. I thought that was wonderful as an idea. Of course, that didn't work that way.
Lots of composers produced music with the Samson box, but Henkjan wanted to do something more. He wanted the box to play music with him.
I wanted to make not only a machine that could make music, but I became interested in, can I have a machine that can listen to me, that can accompany me or somebody else? So I wanted to explain to a machine what is rhythm, what is tempo, when does something slow down or speed up. And then I entered my field, because then it turned out that I, as a musician, couldn't explain to the computer what tempo is.
Henkjan learned of a new field of science called music cognition. He thought this might help him figure out why something like tempo, that was pretty basic for humans, was beyond the capabilities of a computer like the Samson box. So he headed to London to get a PhD in music psychology and learn more about how our minds experience tempo in music.
The tempo is not in the music. The tempo is the music and our mind together make it that we hear a certain regularity or a certain rate or a tempo in it. So this realization that our mind does half of the work what made me a scientist like 30 years ago.
With this knowledge of how our brains allow us to hear music as more than just an assortment of conflicting sounds, he still hoped to make a computer into a musical partner that could understand music like we do.
And then, of course, I try to explain to a machine what tempo was, what rhythm is, timing, when is a note early or late, all those kind of things. And then after a while, that didn't work out. And then I thought, I'll have to know more about the mind, because that's where the key is.
So he spent a few more years pursuing psychology and modeling the mind's perception of music. Then he moved to the University of Amsterdam, where he combined all of his interests in computer science, psychology, and musicology into a new field, adding biology and evolutionary science into the mix, and expanding his questions even more. How far back does musicality go in our evolutionary history? And how much do we share it with other animals? And here is where babies, birds, beats, and Charles Darwin enter our story. Since music is such a universal human experience, figuring out if musicality was something we're born with or something we learn seemed like the perfect place to start.
Everybody has their preferences or their dislikes. Everybody can remember a certain melody. It might even stick in your mind for days. We like certain rhythms and we dislike other rhythms. Some rhythms are groovy or nice to dance to, other rhythms are boring. So we all have these preferences, expectations that are confirmed or violated, and we like that or we might dislike that. And that's a musical talent, just like for language.
And it turns out Henkjan had a colleague named Istvan Linkler who could test whether expectations for rhythms were confirmed or violated. And not only that, he could test it in newborn babies, because he had one of Europe's first newborn baby labs.
And they wanted to do an experiment with sound in that project. And I said, let's try out beat perception, because beat perception is the other component that most of researchers agree upon is a fundamental aspect to musicality. Because without picking up the regularity in the music, you can't synchronize with somebody else. You can't make music together. You can't dance together. You can't do rituals together. You need to be able to pick up from the sound. Where are we? If you want to dance, where's the one? So it is arguably fundamental to music. And I thought, well, let's test that in newborns.
So in 2009, Henkjan and Istvan set up a very gentle study with 14 little newborn babies. With the babies sleeping and parents close at hand, researchers placed soft, open headphones on them, leaving their ears uncovered, while they measured their brain activity with external electrodes. They played recordings of drums like you'd hear in a typical rock song, but sometimes beats were missing. And they measured what happened in the babies' brains as they listened. At the core of this study is the fact that young children and babies move to music before they can speak or sometimes walk. And Henkjan and his collaborators wanted to test whether this is learned from and encouraged by parents, or if humans are born with the capability of linking sounds to movement.
So that's what we tested, and it turned out that these newborn babies, these are 1 or 2 day old babies, they were surprised if you removed the note on the downbeat, on the first beat of the rhythm. And if you did it somewhere else in the rhythm, no surprise. So we could show that they have a high expectation of the downbeat, of the regularity of the music. And if you remove the note there, their brain would say, hey, I missed something, there is something weird here. Their brains have beat perception. They can pick up the regularity in the music.
Were you surprised by that?
I was surprised because I thought that this was a learned thing, and then it was obviously not. I mean, it's still difficult to disentangle. This is the nature-nurture question, which is always, these things are always intermingled in the sense, because their hearing is already functional in the last 3 months of the pregnancy. That's the first thing that's ready. They hear sounds in the womb the last 3 months. So they could have learned it in that period, in that sense that they have heard these regularities and they picked it up and that's what they used. But so we only know that it was active at day 1, but extremely early and long before language arises, long before they get sensitive to word boundaries or things like that.
Whether we tune into rhythm in the womb or not, this study was evidence that beat perception is active very early in life and happens before language.
And it is arguably a musical talent. I mean, you avoid regularity in language. Variation is important for language, just like spectral quality is important for language. In music, you can repeat something all the time, and we like that. You can do one melody and you just continue to do the same melody. if I say the same sentence, if I say the same, it's difficult. If I would have said the same thing, if I would have said the same thing, if I would have said the same thing, it becomes very irritating after a while, already after a few times. Even more so, if I repeat literally a certain sentence a few times, it becomes music. You start listening not to the meaning of the words anymore, but you start to listen to the underlying or emerging musical quality of the melodic pattern and the rhythmic pattern.
This establishment of patterns through repetition is what our minds translate into music. And Henkjan's study suggests we're born with this ability to recognize musical patterns, and we know when to expect the beat.
That changed my thinking again, and I thought, okay, music is not just a cultural artifact. It's not something that we have invented, but it is something that is, parts of it are innate, and even newborns have the talent for that. So it all adds up to this one question, like why do you have music? Why does it move us so much? But also, what is more innate or biological in the sense that you would expect that we share aspects of it with other species as well. So I really got into behavioral biology, neurobiology, and the evolution of music then.
Charles Darwin thought that all animals with backbones should share the ability to perceive, if not enjoy, musical rhythms, because we share similar nervous systems. He also thought that these traits must be very old and a precursor to language that goes way, way back in our shared evolutionary history.
It's just an idea, very difficult to test, even more difficult to prove, or falsify for that matter, but a fascinating idea. Like, is music something recent, human, an invention, or is it something that is based on something that is much older, shared with lots of animals, and maybe older than language? And then I thought, well, I have to figure out whether we share this with other animals. This is the next step.
What about music and musicality do we share with other animals? Humans are so musical that we can make anything with the slightest structure into music. We hear a bird, a ticking clock, falling rain. And to us, that's music.
Yeah, even inanimate objects like trains, we you get this rhythmic feeling, and some people liked it. I liked it personally as a sound, but that's our mind that is doing that work. And with birds, it's a similar question. It's really a question whether certain songs are musical to the bird as well, in the sense, what do they pay attention to? And it turns out that they're listening for very different things than we do as humans.
When humans listen to music, we focus on pitch and rhythm. When we listen to speech, there's less emphasis on pitch and rhythm and more on spectral change.
It's more like the quality of the sound that makes the ooh and the ah and the a, and that's how we understand each other. That's the change in spectrum all the time. And birds actually listen in that way also to music. They listen to the spectral changes all the time, and not so much to pitch and rhythm.
Music is different. If you hear Happy Birthday being played, it doesn't matter if it's on the recorder or the piano. We as humans recognize it's the same song. But this isn't true for birds.
I know that melody. For a bird, same melody, different instrument, different song. And that's something I find intriguing. One component that is still difficult to trace in the animal world is relative pitch. So relative pitch is that you perceive a melody, and then whether it's high or low, or whether it is slow or fast, but you recognize it, oh, that's Happy Birthday. You just recognize the object, the thing.
Happy birthday to you. Love you, Grandma.
And as I said before, for birds, that is a different thing. The melody that's higher is a different bird. That's a different object. To us, it's the same thing. So relative pitch is very important to us. But we don't have very convincing examples of other animals that also have relative pitch.
So in proper evolutionary science fashion, Henkjan turned his attention to primates, to test Darwin's hypothesis by checking out our closest relatives, to see how far back beat perception can be found in our family tree.
if we share that with chimpanzees, then you might reason that the common ancestor that probably also had beat perception. And that's a strategy. You go over all the primates and you see when did it originate. So very simple idea.
And he thought he could maybe collaborate with someone who works with primates and that they could learn about beat perception using the same methods they did with the newborn babies.
Yeah, if I knew what kind of trouble was ahead of me, I wouldn't have started it. And I thought, well, this is a very simple technique. I could now sort of test Darwin's hypothesis. Like, do we share that or do we not share this with other primates?
But you can't really do even a non-invasive headphone experiment with chimps. So Henkjan shifted his focus to macaques. While they're not as closely related to us as chimps are, they're the animal model for the human brain, and much of what we know about epilepsy, Parkinson's, and deafness in humans is due to studies from macaques. So they seemed like a good primate to start with. And he found a collaborator for a non-invasive study with macaques, but it turned out that macaques weren't sensitive to the beat. Macaques don't feel the music like we do. Sort of a strike against Darwin's idea that all animals with backbones can appreciate music, and a point for human uniqueness. Henkjan and his research team hypothesized that beat perception might have gradually evolved in primates, which could still mean that chimps might have it. And this time, Henkjan lucked out and found Yuko Hattori, an assistant professor of cognitive neuroscience for the Center for the Evolutionary Origins of Human Behavior at Kyoto University. And Yuko was able to help test chimpanzees for beat perception.
Yuko is one of the people there who does auditory experiments, so she's interested in what they perceive in terms of sound.
Every day, the chimps are invited to participate in the experiments if they want to.
And they come in, and one chimpanzee is called Aji. She's a female. She was 36 when I was there. And very eager, every day coming in, banging on the window, let's start. And then they had a little game where they could participate. She uses an electronic keyboard.
What Henkjan and Yuko were eventually able to observe was that chimps were able to synchronize with a rhythm on a keyboard. Sure, they weren't the best at it, but it was evidence that the link between our motor and auditory systems goes back deep in our primate lineage. And in fact, chimps in the wild have been observed to do rain dances, where male chimps make rhythmic motions when the rain starts.
Slowly, there seems to be more evidence for this idea that, at least within the primates, it's an gradually evolving thing. So it's not uniquely human, but we share it with other primates.
But primates aren't the only animals that have beat perception. In 2008, a charismatic sulfur-crested cockatoo named Snowball wowed the world by dancing to the Backstreet Boys.
Then we were very skeptical. I thought it was just imitating the owner because you saw a shade on the wall. I thought, well, this bird is just going in sync with somebody dancing in the room. But in 2009, they could show convincingly that Snowball could dance to popular music that he was being exposed to by his owner for a long time. And if the music was faster, Snowball would headbang faster. If the music was slower, Snowball would headbang slower. So he was really paying attention to the music.
Snowball was the first documented case of an animal with beat perception. Snowball was a star, a natural performer, and it was a huge moment for comparative biology and music cognition.
Yeah, so that makes Snowball an important animal model. So since then, more systematic experiments have done with other bird species, and then it turns out that particular kind of bird species can also learn new sounds over life.
This ability to learn and mimic new sounds by listening to others is called vocal learning. Vocal learning is essential to human speech, language, and music.
And that's something we share with cockatoos, but also with parrots and with some songbirds. They're also vocal learners. And in the whole animal world, there are, I think, only 7 or 8 species that are vocal learner.
Other known vocal learners include elephants, whales, dolphins, porpoises, seals, sea lions, and bats. But all in all, very few animals show the capacity for vocal learning.
So it is an enormous reduction of the space of possibilities, because that's the hypothesis that came up since we found Snowball that it might be related to vocal learning. That this idea that we can sort of synchronize or get the regularity out of a sound and synchronize to it, that has to do with the apparatus that is also in use for speech. And that's also, that link, that hypothesis generated also an enormous research activity.
One good way to test a hypothesis is to find evidence to the contrary. So scientists tried to find animals that aren't vocal learners, but still have beat perception.
People tried it with dogs, didn't work out. If you find a dog that can synchronize to the music, it seems impossible. A horse, same thing, not a vocal learner. Horses are not sensitive to the regularity in the sound, so the jockey is really doing the tempo and the speed.
There are like dancing horses.
Yeah, but they are they're listening to their, to their jockey. They can't do it on their own. They can't pick out the regularity from the sound. So that confirms this theory that vocal learning is important.
This brings us to another famous vocal learner, Ronan, the Californian sea lion.
Peter Cook trained this Californian sea lion to different types of music, and in the end also to Earth, Wind and Fire, again very ecologically valid, but still just as a test case. And he could convincingly show, and it has been replicated since then, that Ronan is really paying attention to the music, listening to the music and picking up the tempo.
If you watch Ronan on YouTube, you'll see her shoot up out of her pool and wobble up onto a box, where she waits for the music to start.
And then it was Earth, Wind and Fire, slightly faster, and then on the one, and she was down on the one, and I was too late. So she was very enthusiastic, waiting until the sound started, and then chick, chick, and then she was on. So that was very exciting to see. The enjoyment, the pleasure out of doing that correctly was so apparent. So that made it very convincing to me that it was not a trick that she just learned, but more a behavior that she could turn on and do and enjoy.
And it really does look like Ronan is having a great time. She's dancing, not just keeping a beat, but dancing.
Over energetic, I would say. Like, yes, let's do something. I'm bored. And that also, for some reason, that moved me as well. This enthusiasm about music, but also doing things was sort of very recognizable.
Ronan further confirms Darwin's idea that musicality is shared with other species, and also provides evidence that pleasure and enjoyment is an important part of why we have music.
So it might be that this enjoyment idea is stronger than the vocal learning hypothesis, which might be partially a component that helps or something. But for Snowball, it's the social context that is important for this bird to dance. If the owner is not there, the bird doesn't dance. So it's a social interaction. And that's something that we also have. We can listen to music in solitude, but that's in a way weird behavior. You do most cultures, especially if you look to hunter-gatherer groups. This is a group thing. You sing together. That's what's the function. So the social aspect might be closer to an explanation, I would say, also of synchronization and this generating empathy. If you dance with somebody in sync, you feel more connected.
Without a doubt, music is certainly something that connects us to each other. Recently, Henkjan and an international team of researchers published some Leakey Foundation-supported research with a community of Bayaka people in the Republic of the Congo. They're a modern hunter-gatherer community with deep-rooted musical traditions where spontaneous music making is a big part of everyday life. With community permission, they observed women during their daily group foraging trips, and they learned that the women sang together much more often in groups where everybody didn't know each other already. After collecting data for about 2 years, the team concluded that making music together was a powerful tool used for quickly creating bonds and encouraging cooperation.
And also, it generates endorphin release, so sort of kind of a painkiller, and a social group cohesion enhancer. And that's a clear adaptive, survival-involved mechanism. It might be that music has such an important influence on our rituals or on our group cohesion that it is still there. What I try to do with this work is to show in how far music is not a luxury. We think of music often that it is a luxury, it's a luxury good, but I think it is something very human and maybe even something we share with a lot of animals that has a very long evolutionary history of which we know too little, and we should figure it out.
Henkjan plans to continue his collaborative study with the Bayaka, with a goal of deepening our understanding of the human capacity for music. Thank you to Henkjan Honing for sharing his work. You can learn more about music and musicality in Henkjan's wonderful book, The Evolving Animal Orchestra. You can also find lectures and talks by Dr. Honing on YouTube. We put some links in your show notes. Origin Stories is a project of the Leakey Foundation, a nonprofit dedicated to funding human origins research and sharing discoveries. Support for Origin Stories is provided by listeners like you. Donate today, and your tax-deductible gift will be quadruple matched, including monthly donations. So your $5 a month magically turns into $20 a month for the show. Additional support comes from Leakey Foundation President Jeannie Newman, the Ann and Gordon Getty Foundation, and the Joan and Arnold Travis Education Fund. Click the link in your show notes to donate now and let us know if you'd like a shout out in the next episode. This episode was produced by Ray Pang and me, sound design and mix by Ray Pang. Our editor is Audrey Quinn, theme music by Henry Nagel, additional music by Blue Dot Sessions and Lee Rosevere. Thanks for listening.